Hello and welcome to this video about wave interactions. In this video we're going to look at wave interference, at reflection of waves, and at standing waves. First, let's take a look at an example where we have two billiard balls and they collide. We know that when those two billiard balls collide, they bounce back into different directions from one another. And this is true not just for billiard balls, but for all matter. Matter cannot occupy the same space at the same time. This is not true for waves, however. When different waves collide or come together, they do not bounce back like these billiard balls. In fact, if you think about listening to a band concert and the different sounds at the band concert, you can hear the flute sounds, the sound waves produced by it, and from the French horn or the trumpet, all these different instruments, you hear them at the same time, indicating that the sound waves of each instrument are not affected by the sound waves of the other instruments. Remember that mechanical waves are not matter, but they are the displacement of matter. And for that reason, two waves can occupy the same space at the same time. We call this superposition. Superposition is simply the combination of two waves that overlap. Here we have two different point sources, and the waves that are produced by those are interfering and forming what we call an interference pattern. Mechanical waves are not the only waves that form interference patterns. Visible light and other forms of electromagnetic radiation also undergo superposition and can form interference patterns. So if superposition is the combination of two or more overlapping waves, the superposition principle states that when two or more waves travel through a medium, the resultant wave is the sum of the displacements of the individual waves at each point. Let's take a wave 1 and wave 2, very different waves. The superposition principle states that if these are both traveling along the same place at the same time, we're going to take the sum of each of the displacements at any particular point. So the sum of this displacement and this displacement is going to give us the resultant displacement at each point along the line of time as these waves are traveling down this line. So when we have waves, say we have a wave traveling in this direction and one traveling this direction along this string, we have constructive interference when the displacements are on the same side of the equilibrium position. And so then they can be added together to form the resultant wave. You can see as these get closer, and then as they are actually going through one another in the same position, both of those waves will be added together to form this resultant wave. And then they continue. This wave here, the taller one, is continuing on in this direction, and this shorter wave continues on in this direction as they continue to travel along the string. Destructive interference occurs when the individual displacements are on opposite sides of equilibrium position. And if we think of this as our string again, and we have a wave traveling this direction and a wave traveling this direction, it's on the opposite side of the equilibrium position. When those two waves are actually in the same place at the same time and passing through one another, the resultant wave is going to be the difference between them. And that's what we will see here is the difference. And then those waves continue on in their respective directions. We see complete destructive interference when we have two pulses of equal amplitude, or two waves in this case here, the two sine waves. They have equal amplitude, but their displacements have opposite sign. When they coincide, and we add those displacements together, the resultant wave has a displacement of 0. In other words, the two pulses or the two waves completely cancel each other out. And if this is the situation, it is called complete destructive interference. So far, we've looked at interference produced by two transverse waves or transverse pulse waves. The superposition principle, though, is also valid for longitudinal waves. And when we look at longitudinal waves, just remember Here's a longitudinal wave. You have areas of compression and areas where it is spread out called rarefaction. These are the areas of rarefaction. These are areas of compression. One wavelength would be from one point of this wave to another similar point of this wave. So this could be a wavelength, or from here to here. This is another way to think about these longitudinal waves as well. Areas of compression where the density is higher, and areas of rarefaction where there's lower density. This is simply a redrawing of a transverse wave that is demonstrating this compressional or longitudinal wave. A compression involves a force on a particle in one direction, and a rarefaction would involve a force on that same particle in the opposite direction. So whenever a compression and a rarefaction interfere, there is destructive interference, and the net force on the particle is reduced. Conversely, if we have an area of compression interacting with an area of compression, or an area of rarefaction interacting with an area of rarefaction, you have constructive interference. Just another way of looking at these ideas about interference, we have superposition of two identical transverse waves that are both in phase. That gives us a wave of increased amplitude. If we have the superposition of two identical longitudinal waves that are in phase, that obviously gives us a wave of increased intensity. Two identical transverse waves that are out of phase destroy each other when they're superimposed, and the same thing happens for identical longitudinal waves that are out of phase. They destroy each other when they're superimposed. Another example of interference, here we have this interesting pattern. We can represent, if we have these two sources, these waves are interfering with each other, we can draw a diagram of that where we represent the peaks by a solid line and the troughs by these dashed lines. In this case, then, we have destructive interference when a peak and a trough interact, and that would happen at these points here. You can see that peaks and troughs are interacting at those points. We have constructive interference where we have peak-to-peak interaction or trough-to-trough interaction, and you can see here we have trough-to-trough interaction. Here we have peak-to-peak interaction, and that occurs as we can see along that line. So far, we've been talking about waves that can travel indefinitely without striking anything that would stop them or change their motion in some way. But what happens to the motion of a wave when it hits a boundary? Well, we're going to look at two different situations because the answer is a little bit different for each. First, let's look at a rope or a string right here that is going to be attached to a ring. And you can see that in the diagram here. There's a ring that is going around this post. And let's assume that this ring is free to move up and down this post with very negligible amounts of friction. And we send a pulse along this string, and the pulse is going this direction. We can see the wave here, one wave pulse traveling here. And when the pulse reaches this boundary, the rope is still free to move up as usual, and it pulls the ring up with it. Then, when it gets to this point, the ring falls back down to its previous level. And when it does that, it sends a motion that were similar to a movement that would result if someone were to whip the rope upward to send the pulse initially to the left. And so what we see is that the reflected pulse is traveling back along in the opposite direction, but it is identical to the incident pulse or the original pulse. They are the same. So when the end of the wave is free to move, we have the reflected pulse being identical to the incident pulse. But what happens if the end is fixed? Let's say this string or rope that's attached to this ring the ring is fixed and it is not allowed to move up and down on this post. What happens to the incident pulse when it reaches this fixed end? Well, the rope is exerting a force that is in the upward direction on this post. And the post likewise, or the ring likewise, is exerting a downward force on the rope. So what happens is this. That downward force on the rope causes a displacement in the direction opposite the displacement of the original pulse. And so the pulse is inverted after it is reflected. So the reflected pulse is an inverted pulse from the incident pulse when the end is fixed, when the end of that wave is fixed. Let's take a look at standing waves. If we have a string here and we vibrate it at exactly the right frequency, we can form a standing wave. And the reason we called it a standing wave is because the resultant wave pattern appears to be standing still. We have nodes on a standing wave that are points that always undergo complete destructive interference, so they appear stationary. They remain stationary, actually. The particle there is stationary. The antinode, or antinodes in a standing wave, would be the place where the largest amplitude occurs. So these would be the antinodes. And a standing wave is the resultant wave pattern that doesn't move. In order for it to occur, the two waves, the incident wave as well as the reflected wave, have to have the same frequency, wavelength, and amplitude when they're traveling in opposite directions and interfere with each other. Now, obviously, only certain frequencies can produce standing waves. Those frequencies have to be such that the ends of the string are nodes. You can see in all these different examples, you have to have a node at both ends. So there are only very specific frequencies that will produce this standing wave. Here, the wavelength that allows the correct wavelength to allow the right frequency for a standing wave to occur would be 2 times the length of the string. Here, the wavelength is the length of the string. Here, the wavelength is 2/3 the length of the string, and here the wavelength is 1/2 the length of the string. Here's some advanced ideas. Look up a de Broglie wavelength, do some research on electron microscopes, or maybe you have your own ideas or your own questions. Please feel free to research those, and I look forward to seeing what you come up with. See you in class.